Hi, I'm Paul Liu, and this is our project proposal, Image Machine Learning of Printed Metal Films for EMI Shielding. This is a joint proposal with myself, Satish Iyengar, and Roger French. EMI shielding is becoming increasingly important as more and more electronic components are packed tighter and tighter, and it's important to be able to shield these electronic components from their surroundings. For a lot of applications, EMI shielding also protects humans from the health hazards of certain types of electromagnetic radiation. EMI shielding can also be used to protect sensitive information, and in defense applications, it's important that certain components are protected from EMI pulses. Traditional EMI shielding, as you can see here in the right image, is bulky and consists of metal sheets or Faraday cages. They're expensive to manufacture and they take up a lot of space. This project focuses on printed EMI shields. So here on the left side, you can see a chip, an acrylic layer, insulating layer is printed, and then a metal ink is printed on top of that. This allows for not only flexible electronics, but the creation of EMI shields in a very thin, lightweight form factor. The EMI shields can be created on a variety of complex 3D geometries. After the EMI shields are created, they're characterized through near-field measurements at various radio frequencies. These measurements take about 2 to 3 hours to complete, and so there's a need to be able to predict EMI performance without having to do near-field measurements on every single printed chip. So the objective of this project is to realize a combination of characterization and machine learning techniques to enable the prediction of EMI shielding performance of these printed metal films. The first task focuses on the characterization of the printed metal films. So this seeks to combine characterization of both the topology as well as local sheet conductance measurements. So the topology can be obtained by optical profilometry, and the local sheet conductance can be obtained by 4-point probe measurements or terahertz reflection measurements. The second task focuses on combining the data that we've obtained through topology, local sheet resistance, and near-field performance, and doing some image processing. So you can see here that there's some edge detection that's being done to determine the thickness of the metal that's being deposited, and ultimately predict EMI shielding performance without having to do near-field measurements on every single chip. So this can enable quality control of printed EMI shields. It can also enable perhaps smart printing of EMI shields where more metal can be deposited in certain areas where there's more of a need to protect components or make sure EMI electromagnetic radiation does not get through. The deliverables from this project are data sets from the topology as well as local conductivity of various printed metal structures, and new software will be developed to predict EMI performance from this data.